Hello everyone, my name is Dong. I come from Huazhong University and Science and Technology. Today I will present our work, understanding and detecting fail-slow hardware failure bugs in cloud system. This is a joint work with Purdue University. Hardware failures are widely studied by academia and industrial. Based on the state of the hardware, we can classify it into three categories. The first is the healthy hardware, which means everything is okay. It has no more functionality with the expected performance. The second is the fail-stop hardware. Fail-stop hardware cannot perform no more functionality. For example, software cannot read and write from fail-stop disk. Such hardware failures are widely studied by academia and industrial papers. Moreover, there are many fault injection tools simulate fail-slow hardware to detect failures in cloud system. The third is the emerging fail-slow hardware, which means the hardware is functional with the lower than expected performance. The new type of hardware poses a new challenge to the reliability of cloud systems. Moreover, there is no paper that studies how fail-slow hardware affects cloud systems at a software level. Today, this talk will present this problem. Software hardware is a real-world problem, not a story. It causes severe consequences. For example, in gigabytes, a network NIC can suddenly only transmit at 1 kilobit per second. In early cloud, they found the fail-slow NVMe SSD can degrade to SATA SSD or HDD level performance. Fail-slow hardware is also common. It happens as frequent as fail-stop incidents. Moreover, annual fail-slow failures risk is 1 to 2%. Let's see a real bug in ZooKeeper, which is caused by fail-slow NIC. We can see that the serialized thread acquired the log and synchronized the data to the follow. Is stuck due to the fail-slow NIC. However, the failure detector thread cannot find this problem. It sends heartbeats and gets no more. At this time, the client sends a write-type request such as quit and set to the leader. The request processor in ZooKeeper acquired the log held by the serialized thread. However, the serialized thread is stuck. As a result, the request processor is also stuck. Finally, the client will get the error code from the leader. If the client sends the read-type request, the client will get correct results. In this talk, we define fail-slow hardware failure as the software-level failure caused by fail-slow hardware. Let's go back to this example to see if the failure detector is also affected by the fail-slow NIC. What will happen? If the failure detector is slowed down by the fail-slow NIC, the follow cannot get heartbeats from the leader. Therefore, the follow will exclude the leader from the cluster and start a new leader election, which driven the cluster into a healthy state. And the client will disconnect from the old leader and try to connect with the new cluster, so the previous bug does not occur in this scenario. From this example, we observe a key of characteristics. The fine granularity of fail-slow hardware is necessary to trigger FSH values. To confirm this observation and deeply understanding fail-slow hardware failures, we studied 48 FSH values case from 5 large widely used cloud systems. The functionality of this 5 cloud systems is diverse, including coordination servers, file system, data analytic framework, and a database. After studying these failures, we observed some findings. This figure shows the symptoms of studied failures. We can find that over half of the FS failures cause no service to be unavailable, which means fail-slow hardware cause some functionality or even a node to be stuck. The second finding is about 20% of FSH failures are silent. Detecting these failures requires the specification of a cloud system. Additionally, we find that the root cause of studied failures are diverse. The top 3 root causes are indefinite blocking, buggy internal checker, and data race. Only data race and deadlock belongs to concurrency bug. After diving this root cause, we observe that fail slow hardware causes FS failures due to bad practice of synchronized and timeout mechanisms. This talk takes the synchronized mechanisms as an example. Let's see how a bad synchronized mechanism interacts with fail slow hardware. Event 1 occurs at time 1. This event occurred the lock at time 2. Event 1 becomes very slow due to fail slow hardware. The other event 2 occurs at time 4 and acquire the log held by the event 1 at time 5. Hence, the event 2 will be indefinitely blocked by the event 1. Moreover, the internal checker cannot figure out the reason. More funding can be found in our paper. FS failures cause severe damage in cloud system. So how to deal with FSH failures? There are 2 directions. The first is in production detector, such as Panorama, ASO, Omega Gen, and Perseus. Existing in production detector also detect part of FS failures, but detect FS failures has already caused damage. The other direction is the for injection tools such as FIT, Questioner, Loglas, and Chronos. However, existing for injection tools are inefficient due to overlooking characteristics of FS failures. So we propose our solution, a Sieve, for injection testing framework for cloud system to detect FS failures. Sieve can efficiently explore large for injection space by statically analyzing synchronized and timeout for points. It also enables fine-grained fault injection by automatically instructing hook to precisely simulate fail slow hardware within a system. Here is the Sieve's workload. There are 2 phases. The first is fault point analyzer. Static fault point analyzer takes target cloud system as the input and identifies synchronized and timeout protected fault points, and then fail slow agent instrumentation will instrument hooks at identified fault points, and we will get an instrumented system, and then we enter into the second phase. For injection testing, the workload driver send input and control the execution of the instrument system. The injection controller interacts with fail slow agents and determine whether to detect a fail slow injection. Failure checkers will collect the information from the cloud system and a workload driver to determine whether a bug occurs. This talk focuses on static fault point analyzer, which identifies synchronized and timeout protected fault points. And then I will introduce fail slow agent instrumentation, which is key to enable fine-grained fault injection. Let's see how to identify synchronized fault point. Here is the Java code. The scope from lines 2 to 10 is synchronized critical region. The four points within this scope are synchronized. After translating this Java code into low-level bytecodes, the critical region becomes sequential instructions worked by entering and exit point. However, the branch and the return instruction will introduce more exist point. We need to find the correct exist point so that we can identify the correct critical region. After analyzing many cases, we find the correct exist point should be the last exist point, not followed by return. Next, let's see how to identify timeout-protected 4 points. Here are 3 functions. Function 1 and function 2 record start times and call function 3. Function 3 executes some I/O operations and record n times. To identify timeout scope, we need to match start time to the correct n time. From this example, it's hard to determine which n time is matched to the start time 1. Maybe n times 3 or n times 4. The same problem for the start time 2. However, we observe the timeout mechanism can execute function 4 to calculate elapsed time. Based on the information in function 4, we can identify n times 3 is matched to the n time 1. Hence, the correct timeout scope is found. The 4 points within the time scope are timeout protected. After identifying synchronized and timeout protected 4 points, we need to instruct hooks to precisely simulate for fail-slow hardware. Existing for injection focus on cross-graded for injection. There are 2 common methods. The first is to control the environment. For example, when the method simulates disk fault, all functions related to the disk will fail. The second is to add an interception code in the library. Therefore, all functions with the same signature will fail. Sieve enables fine granularity for injection by instructing hooks at the implementation level. When the fail-slow agent is executed at runtime, it sends the injection to the controller. Evaluation will apply Sieve to 3 cloud systems: ZooKeeper, HDFS, Kafka, and Sieve detects 6 new bugs, 2 of which are confirmed. You can get more detail in our paper. In conclusion, fail-slow hardware causes severe damage in cloud system. Moreover, existing for injection testing is inefficient. To identify how fail-slow hardware affects cloud system, we conduct study on 48 FS failure case. Based on our bug study, we propose Sieve for injection testing to detect failures, and Sieve detects 6 bugs, 2 of which are confirmed. Our bug study and Sieve are open sourced at GitHub. Thank you for your listening. Now I'm ready to take questions.